When some innovative caveman invented the bow and arrow, it was a huge breakthrough. The discovery turned the Homo sapien into an efficient hunter-gatherer. These days, archery has made a comeback in the hunting community, and it's even been reclassified as an Olympic sport. Today's bows are definitely not primitive devices. Crafted with calculated precision, they make it easier for you to take your best shot and hit your intended target. To make a longbow, a craftsman cuts 6 strips of cherry wood, just under 1/4 of an inch, using a bandsaw. Then, with a belt sander, he repeatedly thins the wood strips on both sides, tapering the ends a little each time. The tapering gives the wood some flexibility, which the bow will need to launch arrows into the air. With his bandsaw, he now carves a handle from a piece of wood. Next, he brushes super adhesive glue onto fiberglass strips and the tapered strips of cherry wood. He works swiftly because the glue will start to dry in less than an hour. Now he layers the strips. The fiberglass strips buttress the 6 glued wood strips on either end. This process is called lamination. Next, he glues the wood handle to the fiberglass and wood lamination. And he tops it with a piece of masking tape to protect it from scratches and glue smudges during the next steps. Now the laminates are squeezed together. He places them on a carved plywood shape called a bow form. He positions a steel heat strip, a rubber hose, and another plywood form on top of the laminates. He clamps it all together, then inflates the rubber hose with an air compressor. The pressure from the hose combined with the heat from the metal strip mold the wood to the bow shape as the glue sets. 1 hour later, he removes the laminates, nicely pressed and glued into more bow-like curves. Now he draws the bow form onto the newly curved lamination, following a template made of fiberglass. With his bandsaw, he cuts the wood along the lines he's just drawn. He cuts an arrow shelf. That's the notch for the arrow to rest as the archer aims. Then he trims the handle, making it a little wider at the center for comfort. Next, using a coarse tooth file, he hollows out little grooves in the upper and lower limbs of the bow. They're called string nocks, and the string will loop around them. To strengthen the tips, he glues little pieces of fiberglass and moose horn over them in the freshly filled nocks. He clamps it in a vice grip to set. When it's dry, he files through the horn and fiberglass to bring back the knock groove. He smooths it with sandpaper. Now he glues another piece of wood over the handle to improve the look and feel of it. He clamps it together while the glue dries, and 3 hours later, he sands it. Next, he wraps the handle in a piece of leather and stitches it together with nylon thread called artificial sinew. Many years ago, they used the tendons of an animal for thread. The leather will make the bow easier to grip. With a gel pen, he writes a serial number on the back of the bow along with the draw weight. This bow will hold about 44 pounds of pressure in check when it's drawn. This is a Flemish string jig, a wood fixture with posts on it. He loops nylon string around the posts. This is how he measures the string. It's always 4 inches shorter than the bow. He cuts it with a utility knife, then rolls wax onto it to make it easier to work with. He measures some string. Then he twists 16 strands of nylon, 8 black and 8 white, into a braid with loops on the ends. He hooks the string on the nocks, and it's time for target practice. As he bends the bow, energy is stored. He releases it, and the energy propels the pointed projectile. Right on target.
With all the attention we pay to our car's high-tech parts, it's easy to overlook the importance of a vehicle's bumpers. About 80% of car accidents are front or rear collisions. The bumper is designed to absorb the force of the impact, minimizing damage in low-speed collisions. Bumpers can be made of plastic, fiberglass, aluminum, or steel. This company makes steel bumpers. They start out as blanks, steel sheets just 0.08 of an inch thick. These are en route to becoming truck bumpers. A robot feeds each blank through a series of 7 to 9 dies, depending on the bumper model. Each die stamps the blank into a particular shape using some 2,000 tons of force. This progressively forms the blank into the final bumper shape. Both the front and rear bumpers go through the same process, only with different dies. The bumpers now travel to the next production area, where a worker clamps each one onto a specially designed cart. At this point, the factory paints certain models. These bumpers will get chrome plating. But first, they travel through a series of buffing wheels. The bumper surface must be impeccably smooth because the chrome finish magnifies even the tiniest flaws. A computer-guided crane stacks the bumpers and maneuvers them through the chrome plating process. First, it submerges the bumpers in several cleaning tanks to remove any residue left on the surface from previous operations. The company won't divulge what chemicals it uses to clean the steel, because this surface preparation is the secret to first-rate metal plating. The first plating tank applies a coat of nickel to protect the steel from corrosion. The next tank applies the chrome layer. The factory uses the standard electroplating process. In a water and chemical-filled tank, the plating metal particles get a positive charge, while a negative charge runs through the bumpers. This magnetically draws the particles onto the bumpers in an even layer. After a thorough rinse, the bumpers are inspected. Workers scrutinize the chrome mirror finish under high-intensity light. Meanwhile, this machine pressure injects molten plastic into various molds. A built-in cooling system hardens the plastic within seconds. Then, out comes the plastic components that attach to the bumpers. One of those plastic parts is the step pad that covers the top of the rear bumper. Once the pad's in place, a worker attaches a built-in trailer hitch. Steel mounting brackets help structurally reinforce the bumper. The front bumper goes down a different assembly line. A worker attaches a plastic trim that hangs down just below the bumper. Its aerodynamic shape helps direct airflow to the engine compartment. Next, 4 steel reinforcing brackets that will attach the bumper to the truck's frame. And finally, the license plate holder and fog lamps. Workers tighten all the bolts to a specified tightness. This ensures that the bumper and its mounting brackets will adequately absorb the force of the collision. Whenever a new model goes into production, the first few bumpers off the line go through a battery of tests to prove they can withstand stress, vibration, and a certain degree of what engineers call crash energy. Other types of bumper systems use a combination of springs and energy-absorbing material, such as plastic foam. With either method, the goal is for the bumper to absorb the impact. In a low-impact crash, this should ideally confine the damage to the bumper itself, leaving the headlights, the engine, and the driver unscathed. The ancestor of the modern trumpet was a straight horn that could emit just a few notes. By the 15th century, instrument makers learned how to bend the horn, allowing for more notes to be produced. The invention of the valve in the mid-1800s finally allowed the trumpet to play in any key. A trumpet is made up of 5 feet of tubing. 3 valves allow air to flow through additional tubing to alter the trumpet's pitch. Trumpets are made from sheets of metal, most often brass. This factory combines different thicknesses of brass in a single instrument to attain a particular sound. Workers first lay a template on a brass sheet and trace it out. Then they cut along the score line with electric shears. This piece will become the trumpet's bell. A manually operated press forms a perfect fold down the middle. Then they notch the edges. Then they close up the bell by hammering the notched pieces onto the opposite edge. They use a rawhide mallet because anything harder would damage the brass. A brass alloy is melted along the joint. It solidifies in a metal seam that permanently bonds the edges. Next, the bell goes over a cone-shaped mandrel, where the brass is hammered until it, too, is cone-shaped. Then the bell goes onto another mandrel mounted on a lathe. Here, the brass cone is refined into a more refined shape. Then the metal is filed smooth. Now for the bell's rim, called the bead. A brass rod with a notch at the end catches the edge of the bell and rolls it back into a rim. Metal workers use what's called a concave roller to round the rim's jagged edge. Then they slide a brass alloy wire into the rim pocket. This makes the bell stronger and adds weight to the edge of the flare to project the sound better. They roll the rim over even more to enclose the wire. Now they heat the rim and apply acid flux to clean the surface for soldering. Lead or silver solder ensures the wire won't rattle when the bell vibrates. After wiping off the excess flux, the bell goes back on the lathe to scrape off the excess solder. Using an abrasive sponge, workers smooth away any scratches left by the scraper. Then they remove any solder bits trapped in the rim. Now the entire bell is filled with a soapy solution. Then it's frozen at minus 56 degrees. When the solution is frozen, the bell goes into a bending block. The frozen solution provides counter pressure, preventing the brass from buckling inward. And because there's soap mixed in, the pliable ice doesn't shatter under the pressure. After the angle of the bend is checked with a gauge, the bell is defrosted. In the mounting department, workers assemble smaller components made of brass and nickel. Valve casings, the sliding tubes to which they connect, the slide for tuning the trumpet, the pipe that holds the mouthpiece. Then they solder on the bell. They lubricate 3 pistons and install 1 in each valve casing. These slides have to be loose enough to move, but tight enough to prevent air leaks. 1 slide has a finger ring for holding the trumpet. After polishing and lacquering the brass, workers test the trumpet for sound quality. This is one company that likes to blow its own horn.
The tuba is the largest instrument in the brass family and the one with the lowest pitch. Famous orchestral composers from Stravinsky to Gershwin have included significant parts for tuba in some of their best-known works. Some composers have even written full concertos for tuba. Tubas are made of brass, sometimes silver or gold-plated. The instrument consists of valves and tubing, ending in a flared bell. The bell flare begins as a brass disc, 22 inches in diameter. They use a range of tools and various mandrels to work the brass into a preliminary bell flare shape. They use sandpaper to remove any marks left by the tools, then cut a hole in the center. To make the conical tail that leads to the bell flare, they bend and hammer a thin brass sheet around a tail-shaped mandrel. To join the seam, they cut notches along one edge, then hammer them over the other edge. The artisan then melts filler metal over the seam with a high-temperature gas torch, a process known as brazing. Then they use a wooden mallet to round out the shape. They use a pressure roller to flatten out the mallet dents and further refine the surface. After notching the wider end of the tail, they assemble it to the bell flare. They dab on flux, a chemical that prepares the surface for brazing, then tack the parts together. They hammer down the notches and braze the seam all around. This assembly, now called the bell, goes back on the lathe. Using a belt sander, they flatten all the seams flush with the surface. On another mandrel with lubricant assisting the process, they finalize the bell's shape. Now they trim the edge to the correct diameter. Bend it back a bit. Polish the perimeter with the sanding head, then use a special tool to roll the edge over itself. This forms what's called the bell bead, a lip that reinforces the bell and gives this end of the instrument a finished look. A computer-guided engraving machine puts the company logo and model number on the bell. Each of the tuba's 100 or so tubes must be bent into a specific shape. The first step is to fill them with hot liquid pitch, which hardens as it cools. This keeps the tubes from collapsing as they're bent. After bending, the tubes go into an oven to melt out the pitch. Certain bent tubes are enlarged in a machine called a hydraulic blowout press. It pumps oil into it at high pressure. This blows the tube walls outward against the die, forcing it to assume the new shape. Certain bent tubes are conical, others cylindrical. The cylindrical ones go through what's called a ball-out operation. This machine forces steel balls of the proper diameter through the tube. This enlarges any spots that are too narrow. Before bending, certain tubes have to go through a drawing machine for resizing. With lubricant easing the way, it draws the tube between an inner mandrel and an outer washer. This forms the tube to the correct diameters and wall thickness, while also stretching it lengthwise. Coming up next, we'll see where this tube fits in the finished instrument. Tubas come in different versions. A B-flat tuba, for example, is nearly 18 feet long, whereas an F tuba is about 11.5 feet long. Tubas have anywhere from 3 to 6 valves. Pressing different valve combinations produces different notes. To build the valve section, they insert parts called knuckles into the valve cases. Spacers hold the valve cases the proper distance apart, while this alignment plate positions the cases in the correct configuration. Next, they insert connectors to later link the valve section to the rest of the instrument. After brazing the parts together, they run a cutter through the valve cases to hollow them out. Here you can see what the case interiors look like before cutting and after. Now they begin soldering on the valve section's tubing, working from the valve cases outward. The tuba's frame section is made up of several U-shaped parts. Workers assemble them with connecting rings. They insert a support brace inside this frame piece. Then position tabs onto which they'll later mount the valve section. They clamp the tabs in place, then solder them on. Then they attach the bell section to the frame. Before adding the valve section, they give a preliminary buffing to what they've assembled so far. They brush some liquid polishing compound into the places that they couldn't access with the wheel, and buff those areas with a rag. Then a final overall buffing, until the brass reflects like a mirror. Meanwhile, the valve section assembly continues. First, they close off the bottom of each valve case with the screw-on cap. Then drop in a spring to provide resistance for the valve piston. Then the piston. A felt to cushion it. A top cap. Another cushioning felt. And finally, the finger button. A little oil ensures all the buttons move smoothly. The felts inside prevent the pistons from making a clanging sound as they move up and down. Now for the tuba's tuning slides. A coat of grease helps them move in and out to increase or decrease the overall length of the tubing. Shortening tunes the instrument higher, lengthening tunes it lower. Now they screw the finished valve section to the assembled frame and bell sections and insert the main tuning slide. Finally, the tuba's mouthpipe, made not of brass like the rest, but of nickel silver. They spray the entire instrument with cleaning solution to remove any grease residue and fingerprints. Prior to assembly, each section was cleaned and coated with a clear lacquer to ensure the tuba will always look as good as it sounds. Looms for hand-weaving cloth have become increasingly sophisticated over time, but the basic concept still remains the same. Weaving horizontal threads, called weft threads, through vertical threads, called warp threads, to create the patterns in the cloth. The loom lifts selected warp threads. The weaver passes the weft thread between the warp threads, then uses a beater to pack the weft tightly. They construct the loom's frame out of ash, which is strong enough to withstand the pulling of up to thousands of threads. Workers submerge the frame pieces in mineral oil to prevent the wood from drying out. They assemble the frame pieces with heavy-duty nuts and bolts, then mount high-strength plastic brackets for attaching the various components, such as the cloth beam that grabs and moves the finished cloth. They wrap sandpaper around the beam's adhesive surface to grab the cloth without damaging it. Elsewhere, workers make the loom's cables out of high-strength stainless steel. These cables maneuver harnesses that lift and lower the warp threads. After cutting each cable to length, she forms a loop through a cable crimp. Then she locks the loop with this heavy-duty crimping tool. On one of the frame pieces, they mount a metal plate bearing the loom's model and serial numbers. They assemble the pulley system on which the harness cables run. They thread the plastic pulleys onto a steel axle and position the axle with steel discs called stop collars. A spring lever helps each harness lift its respective warp thread. After hammering a pin into each lever, they hook a wire to the pin. Then squeeze the wire closed so that it can't unhook. They attach a chain to an eyelet on one side of the spring lever. Shortening or lengthening this chain adjusts the tension of the harness. Like the pulleys, the spring levers go onto an axle across the loom's frame. Another loom component called the warp beam has holes which hold metal hoops that guide the warp threads. A brake drum on the side provides counterforce to keep the threads taut. At the front of the loom, they install foot pedals called treadles. The weaver uses them to lift and lower the warp threads. Next comes the beater, which the weaver uses to pack the weft thread into the fabric. The pulley system for the harness cables goes on top. This computer-controlled device, called a dobby head, lifts and lowers the warp threads according to the programmed weaving pattern. Each harness cable hooks onto the dobby head, goes around one of the pulleys, and attaches to a hook on the harness. The factory checks every dobby head on a test loom to ensure the device outputs the programmed patterns correctly. Next, workers install the spring levers that help the harness lift the warp threads. Each lever hooks onto a spring, which attaches to a chain, which connects to a harness. They install the warp beam at the back of the loom. The weaver installs the hoops and warp threads on the warp beam. As the loom weaves, the cloth beam gently moves the emerging fabric forward. The weft thread is wrapped around a bobbin called a shuttle. This pattern requires a two-weft thread technique that uses a second shuttle suspended in front of the weaver. The loom keeps the threads evenly taut, producing a consistent and uniform weave, the hallmarks of a beautiful quality cloth.